Hi everyone, we're going to continue talking about basic differentiation rules. So in our first example, we're asked to sketch the graph of a function such that the derivative is less than zero, meaning that the derivative is negative, right? And the rate of change of the function is increasing. Remember, rate of change is the same thing as slope or the same thing as derivative or whatever. Okay, so I want the derivative of my function to be increasing, but I want it to be negative. Right, so there's a couple ways we can think about this. If it's increasing and it's negative, then that means it's getting less negative. Or you can think about it as it's approaching zero, meaning that it's approaching the positive numbers. Right, so I basically, on a number line, I want it to be approaching zero. Okay, it's getting more positive, it's getting less negative, it's increasing. Okay, so actually doing this, we can think about all that local linearization stuff. Okay, so remember the slope of a tangent, if we can draw a bunch of them, it'll make a curve. So let's start with a very negative tangent line. Right, so this is very negative, it's decreasing very quickly. And I draw another tangent line that's decreasing less quickly. And another one, and another one. All right, and this right here is about zero. Right, so remember I want it to be approaching zero. And so it looks like if I draw a curve that follows this trend, that it will satisfy my conditions. So I can just draw any graph. Starts off steep and it ends up getting less steep. Looks like some kind of exponential function, right? But it's decaying, right? And it looks like we're done with that example. Okay, next one, I want to find a and b so that this function is differentiable everywhere. All right, if it's differentiable, there's a couple things I know. First of all, if it's differentiable, I know that it's continuous, right? So all those conditions of continuity, those would all apply here, right? And I also know that the limit as x approaches, in this case 2, because 2 is where my function breaks, right? 2 from the left of my derivative has to equal the limit as x approaches 2 from the right of my derivative, right? And I know this because basically on any given graph, okay, the derivatives act very much like they follow very similar rules to continuity, meaning that again you can't have a sharp turn. The reason why you cannot have a sharp turn is because at this point the limit from the left and the limit from the right of the derivative are very different numbers. Okay, so that's why you cannot have a sharp turn, because the limits have to be equal. Very similar to continuity. All right, so let's actually get this in equation form. So I know that the limit as x approaches 2 from the left of my derivative. So 2 from the left will be using this top function. So my derivative will be 2ax has to equal the limit as x approaches 2 from the right of my function, which in this case will be the bottom one, and it's just b. Right? If we plug 2 in, that means that 4a has to equal b. Okay, and because it's continuous, I also know that my functions, these two functions have to equal each other at 2. So that means that 4a plus 1 has to equal 2b minus 3. All I did was I plugged 2 in for x because I know I'm solving for a and b. Right, so I have these two equations here and I have two variables. So again, good thing. So you have a system, we can solve it however. I think it'd be easiest to substitute. So let's substitute b for 4a. All right, all I did was I know b is the same thing as 4a, so I substituted. Okay, so let's simplify some. Okay, so that means that 4a equals 4, so a has to equal 1. Okay, and if a equals 1, I know that b is 4 times that, so b has to be 4. Okay, so these are the two answers to my question here. Let's keep going. All right, last example, I got an application. Okay, so this is a very common application. At time 0, some dude is jumping into water. All right, and they give me a very standard physics equation right here. This is my position equation, where v naught is my initial velocity, s naught is my initial position. So if I plug in the values that they give me, I have my position equation, right? This is my position equation. So first I'm asked where the diver hits the water, right? So I can plug 0 in for my position because that's like the ground. Okay, so in this parabola here, 0 is going to be where the water is. I want to know where my position is 0, so I can plug 0 in for y and solve for t. So the easiest way would be to factor out a 16. All right, we can solve this. Let's practice using our calculators a little bit. So if I go to my calculator and I go to my y, let's turn it on, and I go to my y equals. All right, and if I go to my graph, okay, if I go to my graph, I see I have some parabola. So this is the position of the diver over time. He hit the water right here. All right, so you could trace, but that's probably the crappiest way to solve this ever. You know all about the second trace menu, so you could use 0. Alternatively, you can use the solver. So let's take a look at that just in case you've never seen it before. To use the solver, you hit the math button, you go all the way to the bottom. And something that's really handy about these TI-84s is that we have all these alpha menus. We talked about that a little in class. If I hit alpha trace, right, I can recall any variable or any equation that's in my y equals. All right, so here y1 is my equation. So in my solver, I don't want to rewrite my equation because I've already written it once. So I can just recall it anytime I want. So I'm recalling y1. I go down, I hit alpha, enter. I want this green solve function, and I get 2. Right, so we could have solved that, but I end up getting 2. So t is 2 seconds. Very important to include your units. You will get deducted for that if you forget them. All right, for part B, I want to find the instantaneous velocity. Right, so I'm given position, but I want to find velocity. Now the handy thing is that the derivative of position is my velocity. Okay, that's something that I know. That's the relationship between position and velocity. The derivative of position is velocity. So let's find the derivative. Okay, the derivative, I just multiply this by 2, so negative 32t plus 16. All right, this is my velocity. I want to evaluate at 1. So v of 1 is going to be negative 32 plus 16, which is negative 16. Right, so this is the velocity at 1 second. Okay, not like between 0 and 1 or anything like that. At 1 second, he's going exactly negative 16 feet per second. Okay, there is a way to do this on your calculator, so let's go through that. You go to your home screen, and again, these alpha menus are really handy. So if we hit alpha window, and my third option is the derivative. All right, so you get this, and you recognize this notation by now. Right, I'm taking a derivative with respect to x of my function. Now again, I don't want to write it again, so I'm just going to recall it using my alpha menu. So I'm taking the derivative with respect to x of y1 at x equals 1. And if I did everything right, I should get the same answer, so negative 16 feet per second. Okay, last question, I want to find the average velocity. So this is average over a period of time, between 1 second and 2 seconds. I want to know his average velocity or speed, basically. Hey, they're similar concepts. Just speed doesn't have direction. So what I can do this in my calculator as well. Let's practice. If I hit alpha y equals, I can make a fraction very easily. Okay, and what I can do is I can, again, just keep recalling my y1 function. And if you put parentheses and a number inside, okay, just like you would write, it's like f of 2, in this case y1 of 2, it's going to plug 2 into your y1 function and evaluate it for you. Right, so it makes it really handy to do problems like this. So I'm going to keep recalling my y function, plugging in what I need to. That's the top, bottom is 2 minus 1. Remember, this is just slope. So it's the difference of my y's on top, the difference of my x's on bottom. I hit enter and I get negative 32 for my answer. Right, so I know my average velocity is negative 32 feet per second. And again, the difference is this is instantaneous. This is 1 split second in time. This is over a period of time between 1 and 2 seconds. Right, that's it for these notes. I'll see you all later.